Great. So, yeah, so very happy to have our second speaker today, David Hawkins from Notre Dame. We're talking about set-theoretic forces in computational practice.
Well, thank you very much. So those of you who know me know that I wear many hats, and I mean that literally and also figuratively, because sometimes I'm a philosopher and sometimes I'm a mathematician and sometimes I'm a set theorist, a logician, and so on. And today I'm going to be putting on my computability theory hat, and so I thank you very much for welcoming me to the computability seminar over here. But also it's going to be computable model theory and also set theory because it's about forcing. So I hope you enjoy it. So let me jump right in. Let's see, is this working?
I like the rim of your hat.
Oh, thank you.
So it's click on the slide.
Okay, there we go. Okay, so this is joint work with myself and Russell Miller and Cameron Williams, and our papers on the archive with the title Forcing as a Computational Process. And so, of course, the method of forcing is ubiquitous. Within set theory, we use it all over the place. We build diverse models of set theory, revealing this vast realm of set-theoretic possibility. Of course, we can make models of set theory with the continuum hypothesis or without, or with system trees or without, all different kinds of models with definable well orderings or without, and so on, all achieved by forcing. But at the same time, the method has an algebraic character, and I'll explain what I mean by that. So for any model of set theory M, we can construct forcing extensions M of G by adjoining this ideal object G, the generic filter. It's something like a field extension. And everything in the forcing extension is constructible directly from objects in the ground model from this new ideal object G, constructible in a very concrete way. And so the question that I want to address is something that I proposed years ago, is that we should mount an analysis of forcing from the perspective of computable structure theory. I want to do the computable model theory of models of set theory, particularly thinking about forcing. And so, to what extent can forcing be seen as a computationally effective process? That's the main theme of the theorems. And to make it more precise, so given an oracle for a countable model of set theory M, to what extent can we compute its various forcing extensions M and G to produce oracles for those forcing extension models? Okay, so the answer is going to depend on exactly how we're given the model M and how much of it we're given, what part of its diagram we're given, and so on. So let me explain. The main conclusions will be, we're going to get affirmative answers in certain senses. If I have an oracle, even only for the atomic diagram of M, this is a model of ZFC, say, or you can actually make do with much less than CFC. So if I have an oracle for the atomic diagram of the model of set theory M, and I have a forcing notion P inside M, and by that I just mean a partial order, then we can compute from that oracle an M-generic filter for that coset from just the atomic diagram. If we have the delta zero diagram of M, and since I realize I'm talking with computability theorists, then let me emphasize that I'm talking about the set-theoretic notion of delta zero here, not the arithmetic notion of delta zero. And it's very different from a computational point of view, because of course in arithmetic, in the natural numbers, then if you know the atomic diagram, you can compute delta zero truth because all the quantifiers are bounded. But in set theory, we also mean bounded quantifiers, but those bounds are themselves infinite, and so you cannot compute the delta zero diagram of the model generally just from the atomic diagram. It's really much more information. So in this talk, whenever I say delta zero diagram, I'm always talking about delta zero in the Levy sense, in the set theory sense, not in the arithmetic hierarchy sense. So, okay, if I have the delta zero diagram of the model of set theory, then I can uniformly compute the delta zero diagram of the forcing extension that arises from the generic filter that we built in the first part. And if I have the full diagram of the ground model M, then I can uniformly compute the full diagram of the forcing extension that arises. Okay, but in other senses, the answer is negative. So there's no computable procedure or even Borel construction that is functorial in the sense that if I give you different presentations of the same model, it will produce isomorphic forcing extensions. So that there is no computable procedure that tells me a specific forcing extension. It's always highly dependent on the presentation of the original. Okay, so that's a kind of negative result. So let me get into how this goes.
So you're saying it's not uniform,
Yes, but it's
but it's just stronger than
it's
that.
sort of worse than that. Yeah,
It's not Borel.
it's not even Borel. You cannot do it with a Borel. But in some cases, for some M, you can computably. So it will depend on the model and so. In other words, there are models of set theory that have the property, and I'll get to this thing later, that in any oracle for that model, I get.
So it's highly dependent on the work of the model in the extent.
In the general case, it depends on the presentation, even if you're using Borel constructability. But for some models, it's not like that.
So could you go back to the last
Sure.
page for a second? Okay, and when you say that, so in the different. Okay, thanks.
So, but the forcing extension need not be Borel, right? I mean, it's generic.
These are countable models. The forcing extension is a
Okay,
real,
okay.
it's a countable thing. So we're not talking about the forcing extension itself being Borel. We're talking about the process of taking an oracle.
Okay,
for-
within ZFC, what happens?
Yeah.
So living inside ZFC with these models, okay.
Okay. Okay, so the first thing is that the atomic diagram doesn't know anything. It doesn't know any set theory hardly. Okay, so let me convince you of that. Suppose we're given an atomic diagram of the model. I mean, of course, in some sense, it knows everything because, of course, it's determining the isomorphism type of the model. The atomic diagram, in some sense, is the model. But if all you have is the atomic diagram, you can't really learn very much about the model from it. So the atomic diagram, of course, what I mean is that it has all the positive instances of the set membership relation and the negative instances of the set membership relation. And so I can compute when one number is coded with another. Of course, I'm thinking about using it as an oracle. So the domain of the model is the natural numbers, and I have this binary relation epsilon on the natural numbers, and I can tell when one number is representing a set that's an element of another set, and so on. So the empty set, the number that's coding the empty set, is the unique number that doesn't have any predecessors in this relation. Okay. So it turns out very little is computable. From that, we cannot even identify a single fixed element, a single fixed set. For example, in any countable model of set theory, in any element of that model, there's no algorithm that will pick it out, that will pick out the index of that set. For example, the empty set. You cannot recognize the empty set from the atomic diagram, because of course, maybe it looks like it's empty so far, it doesn't have any elements yet. But, you know, I could rearrange the coding so that that set that you said was coding the empty set actually wasn't, by putting some elements into it and then extending that to a code of the whole universe. Okay, so we cannot reliably find the empty set or omega or the reals or any particular set. So there's no particular set that you can computably say, yes, I've got it, the index.
But I mean, what you're saying here is that these sets are just not, they're not delta zero defined.
Well, you're saying delta zero, but I think you mean delta zero in the. They are delta zero definable in set theory. That's the basic theorem. All of these sets, the empty set is the unique set with no elements.
Yeah, but it's that say that you have to say for all X is not in the set.
You have to say for that for every element of it. So I mean delta zero in set theory. That's exactly why I want to make this distinction between delta zero in arithmetic, which I'm never talking about, and delta zero in set theory, which has a different meaning. So bounded quantifiers in set theory are not necessarily computable because there's this infinitary aspect, even though they're still bounded.
When you say, sorry, when you say B and M, I mean, you mean a set that's definable from the outside, right? I mean,
It might not be definable, but I can point at a set like the empty set or the reals or the power set of
right,
reals or whatever.
Right, but I mean, if you just take an arbitrary element, I mean, how can you identify the element within M, right?
It has an index in M, but real numbers, CFC proves is a unique set of all the real numbers. That's a B.
Right. So
And
there's
the point is that if all you know is the atomic diagram of M, you cannot recognize any such set. Let me give you the proof. I think it's here. Yeah. Okay.
The proof
So-
must be because it's really not delta zero in arithmetic.
Wait.
yeah.
Right, go on.
Yeah, basically, yes. That's exactly the proof. So, well, no, there's some set theory involved. I mean, we have to know that every finite piece of the delta zero the atomic diagram of the model could be extended to a whole presentation. I'm sorry. Any finite piece of the model has many, many copies. Any finite piece of the atomic diagram of the model occurs where that element is representing another set. You have a set, it looks like the empty set, so it doesn't have any members and it's an element of finitely many other things and so on. But that same finite picture of the atomic diagram occurs all over the place. And so therefore I could change whether that index is actually coding the empty set or the real numbers or whatever. By adding index, right? So it's basically trivial. So only finally much of the atomic diagram is inspected, but we can find an alternative presentation of the model in which that finite piece is representing some other set and not the original B. Okay, so it's not just about delta zero. I think it's really.
I mean, basically, it's about definability and arithmetic in some sense, because they all have sigma one definitions, right? But for everything, something happens, right? And they're not so. Right.
Okay,
But we're on the same page.
okay, good. So, right. Okay, so basically the main conclusion of that is that the atomic diagram isn't really the right oracle to be using in the usual case because it doesn't know enough about set theory. It doesn't know enough set. But yet, with forcing, we will be able to construct generic filters just from the atomic. It's actually kind of surprising. You don't need
So with your model you're constructing, you also don't know where the empty set is.
right.
Right? So
Yes.
you're not gaining anything. You'll know.
It's true, yes. If you want to have the delta zero diagram, I mean the set-theoretic delta zero diagram of the forcing extension, then you need to have the delta zero diagram.
I mean, you're getting the atomic diagram in the delta zero
No,
diagram.
you cannot do it at all. If all you have is atomic diagram, it's useless. You can't build the extension. So you really need delta zero. Okay. So if you consider, let me just give you sort of background on forcing, right? If you have a model of set theory M, I mean a model of CFC, right? So that's a set with a binary relation, the epsilon relation that satisfies the CFC axioms. A forcing notion is just a partial order. So conditions, by the term condition, I mean elements of that partial order, and the stronger conditions are lower in the order. Then a filter is generic if for every dense subset of the partial order that's in M, there's some condition in that dense set that's in the filter. And so to be M generic means to meet every dense set in M. And then we're going to build the forcing extension M of G from the P names that are in M using G. You have to do it in a very particular way. If you do it in the kind of traditional way of the value recursion, it won't work. You need to be more sophisticated. Okay, so how to find a generic filter? Well, if we have a countable model of CFC, this is of course the first thing that you do when you're learning forcing is how do you find an M generic filter over a countable model M? And you enumerate all the dense sets. Since the model itself is countable, you can enumerate those dense sets in an omega sequence. And then you build a descending sequence of conditions where at stage n, you get inside the dense set. So that's a descending sequence of conditions that generates a filter in the partial order. And it's going to be generic precisely because at stage n, we got into the dense set. Okay, so that's completely standard. Basically, it's a proof of the Baire category theorem that we're doing here. Okay, so the filter generated by those conditions will be an M generic. Okay. Well, now we can carry out that construction using an oracle for the delta zero diagram of the model because the oracle itself is, of course, listing out the entire model, and so it's in effect giving me the enumeration of the dense sets. So I can ask the oracle if there's an element of the forcing. The forcing is a set in the model. It has an index. I'm fixing that index, and I'm looking for an element of it that is also in the next dense set. Well, actually, I don't even care if it's dense or not. What I'm really asking is just, a given index is coding a set, and if there is a P0 in the set represented by, if I can find a condition that's both in the poset and in that set, then I might, and it's below my earlier ones, then that's exactly what I want to do. And those are all delta zero questions to ask delta zero in set theory, not in arithmetic, because it's an infinite rating. So I can ask, is there a condition in that set that's below my current condition? And if there is, I can extend that way. And I just do that through all the indices. And therefore, I've also met all the dense sets. Okay, so therefore we can compute the filter generated by those conditions. Okay, so this is the first version where I'm using the delta zero diagram, but I told you if we don't actually need the delta zero diagram, we can actually do it with the atomic diagram. And so let me give that argument. So if all I have is an oracle for the atomic diagram, which as we said, doesn't know any set theory hardly, I can still compute the generic filter. So let me describe how that goes. Okay, so fix an oracle for the atomic diagram, fix the partial order P. So we can decide membership in P, because that's exactly what the atomic diagram tells us. And now fix an index for the order. The order is a set inside the model, and so it's represented by some number in the presentation. And I claim then we're going to be able to recognize when P is less or equal Q with respect to the order. And that's actually a little more irritating than you might think at first, because it's not directly a membership question, but we have to code the pairs, right? And so if we could use, say, the Kuratowski pairing, where the order pair PQ is this singleton-doubleton set. So I have to recognize, I have P and Q, and I want to tell if the pair PQ is an element of the relation less or equal sub P. But the less or equal relation is consisting of a bunch of sets only. It's a binary relation, but it's just, I can only ask membership. So I have to search to find an element of the less or equal relation that is a set that has two elements, one of which is a set that has P as an element, and the other of which is a set that has both P and Q as an element. And I can sort of recognize it. So when P and Q are different, then I know that I found the ordered pair PQ is an element of less or equal. So it's this irritating thing having to do with the details of the coding of the pairing function. And if you use some of the other standard pairing functions, then it's not true. You can't compute it from the other ones. Okay. So, but for the Kuratowski pairing, we can do it, and that's a perfectly normal one to be using. Okay, now we fix a set that's representing the set of all dense sets in the partial order. So I can recognize whether I've got the code, an index for something that the model thinks is a dense set. And now I'm going to try to build the descending sequence, and I'm going to try to get inside all those dense sets. So at stage n, I have my previous condition, and I've got the nth dense set that I'm considering, and I'm going to ask, is there an extension of the current condition? So for that, I have to unwrap the Kuratowski thing to see if it's extending it. That's also inside D sub n. Okay, but you can do this. Okay, and that's going to be enumerating the filter, but to make it computable, I should also use the index of the incompatibility relation on the forcing function. Okay, so I have these parameters, one for the order itself, one for the binary relation of the order, and one for the incompatibility relation on the order. And then I can recognize that something's not in the generic filter if it's incompatible with something that is in the
So the really quote non-uniform part is this third paragraph, where you fix the set representing the set of dense sets.
No, that's just one more parameter. I've already got two parameters here for the post set.
So we don't like the girls because it's
Right, I mean, this is the one that I would have not guessed before, right, when I saw the previous.
Right, I think the more unusual one is the incompatibility relation.
Oh,
So
right, because you are.
that's another parameter that I need. So I've got four parameters in this argument. Okay.
so how do you use the incompatibility?
Something is not in G if it's incompatible with
Okay.
something in G. Because it's
Okay,
generic,
okay,
that's
okay,
equivalent.
okay. But in all these cases, right, you just pick oracles in some sense that really gave you the information you needed.
It's not an oracle, it's a point.
Yeah, it's a point, I know. But
It's a
but
point in
but
the
also
model.
you're dealing,
Because these are models of set theory, so it has as an element, which is to say a number,
yes.
the number that represents the incompatibility relation on the coset. So it's not an oracle, it's a parameter.
Yes.
Okay. So it's not uniform as we've been discussing in several senses. It used these parameters P, let's equal P, and independent. I said four. Let's see, what was the fourth one? Oh yeah, this
The dense
the
sets.
set of all dense sets. Okay, and in general, we can't compute this from the atomic diagram because we can't compute any particular object from the atomic diagram as we observed before. So those are required as parameters. Okay, but also the G depends on the presentation, because if I rearrange G, if I just permute, then of course the order of the dense sets is going to be changed, and I might end up picking a different descending sequence, totally different one. Could even be that the M of G prime that you build that way is not even elementarily equivalent to the M of G that you get the other way. So it's highly sensitive to the order in which the presentation is made. Also, this irritating thing about the pairing function, it matters which pairing function you use. Okay. And I mean, actually, in a sense, the pairing function isn't part of the model. And so I can use whatever pairing function I want. The model has sets that represent the pairs for all the different notions of pairing. They're all definable in set theory, and the Kuratowski is one of them. So maybe this doesn't quite belong on this list, because I can pick the index that's using that pairing function. It's not something that's part of the model. It's just part of the algorithm. Okay, so in the last section of the talk, I'm going to consider whether true uniform construction is possible. Okay, so let's continue, because we haven't built the forcing extension. We've only got the filter so far, but I want to build M of G. So what is a P name? Well, a P name is a bunch of pairs, sigma comma P, where sigma is a P name and P is the condition. And the meaning of this P name is if you have a bunch of those pairs, then sigma comma P is an element. It's sort of telling you the kind of credence that you should have for putting the set named by sigma into the set that you're trying to name, right? So it's sort of probability. Sigma is going to be in the set with probability P, not really probability. It's not really credence, it's forcing. So if P is in the generic filter, then that's going to be sufficient to force that sigma is in the set that's being named. Okay, so this is a recursive definition on rank, right? It looks circular, but it's not, because sigma is going to have a lower set-theoretic rank than the name in which it appears. And so it's a recursive definition by transfinite recursion. Okay. The property of being a P name is delta one. I mean, delta one in the set theory sense, not the arithmetic sense. Because to be a P name means that it consists of pairs whose first coordinate is P names, and those things hereditarily. So I should have a kind of ranking function on the hereditary elements of the name in such a way that tells me exactly how the things arise. Or maybe you can think about it like this. Something is a P name if there is a well-founded tree with the property that there's labels on that tree with the elements of the name as they arise, and the given name is at the very top. Okay, so that would be a sigma one account of it, but also all of the trees that obey that recursive rule are going to come to the same result. So that's going to be a quadron account. So that's why it's delta. Okay. Or here's a different account. For anything sigma that you're trying to see if it's a name or not, then look for a transitive set that thinks it's a P name. And that's whether something is a P name or not is going to be absolute to any transitive set. So I'm just searching for a transitive set, but being transitive is itself, I mean, you just have to say every element of an element is an element. That's a delta zero property. So I'm looking for a witness that satisfies that delta zero property plus the satisfaction relation thinks that that sigma is a P name. Okay. So let's build the forcing extension. How do we do it? Well, a very common approach, the sort of traditional approach to building the forcing extension is, first of all, you start always with a countable transitive model. It's a well-founded model. And then you define this value function. So the value of a name by a filter is just the set of the values of the names that meet the winning condition that they got in with a credence that's in the generic filter. So if tau comma P is an element of sigma and P is made it into the generic filter, then I want to put the value of tau into the value of sigma. This recursion is not performed inside the model. This is a meta-theoretic recursion. It's from outside the model. And it only makes sense if the model is well-founded. This definition does not work if the model's not well-founded. So if this is how you understand forcing, then you don't have an account of forcing extensions of ill-founded models, because this definition only works for well-founded models because the recursion is taking place outside them. Okay. But we want to do forcing over every countable model, not just the well-founded countable models. And so we're going to do something else. Oh, I think I talked about here. It doesn't work with all models. The recursion takes place outside the model. It's not a well-founded recursion if the model isn't well-founded. This is not a well-founded recursion. It doesn't make sense.
But
Yes.
earlier on the previous slide, which you don't have to go back to, but didn't you say something about that you already used the fact that you can recognize that it's only still founded because otherwise you don't know whether it's a P name? I mean, you said that, you said you have this well-founded tree.
Yeah, but that is the well, it only has to be that's the internal notion of well-founded. But now we're talking about the sort of external model theoretic notion of well-founded. Inside CFC, we can talk about well-founded trees, and that's the kind of well-foundedness I was talking about in that argument. Right. For something to be a P name is definable in set theory, and it has to do with those trees and well-founded and so on. But those trees might not actually be well-founded. It's just that the model of set theory thinks they're well-founded because it has a ranking function into its ordinals, but its ordinals might not be well-founded if it's not a well-founded model, right? Okay. So I want to understand the forcing over any model of set theory, or because we're using them as oracles over any countable model of set theory, including the ill-founded models. So let's construct the forcing extension instead as a Boolean ultrapower. This is a method that goes back to Vopenka in the earliest days of forcing. So let's consider the forcing relations. P forces the quality, or P forces the sigma as an element of tau. These are definable relations. And now, if I have an ultrafilter, the forcing notion that I can define an equivalence relation. Sigma is equivalent to tau if there's something forcing that they're equal, and sigma is epsilon sub g tau. It's a member of tau if there's a condition forcing it. Then you can prove that that equivalence relation is a congruence with respect to this membership relation, and so you can define the forcing extension simply as the quotient structure by that equivalence relation. So there's no value recursion taking place in the meta theory. It's just a straight model theoretic construction. It's a quotient construction by an equivalence relation. So the construction works with any ultrafilter. Actually, if you have a Boolean algebra, if you do it with a Boolean algebra instead of just a coset, then you don't even need genericity for this construction to work. It will produce a model of set theory, a model of ZFC, just using any ultrafilter. This is a generalization of the Walsh construction, the model theoretic construction. Of course, the ordinary use of ultrapowers in logic and model theory is always on the power set algebra, but you can define the ultrapower by any Boolean algebra, and that's what the Boolean ultrapower is about, and there's no need for genericity. And in fact, you can define the forcing extension without ever talking about genericity or the generic filter. If you take the Boolean ultrapower, you're just defining a certain equivalence relation with has a certain Boolean value. So the equivalence relation is sigma is equivalent to tau if the Boolean value that they're equal is in the ultrafilter, which isn't necessarily generic. It's just any ultrafilter, even an element of n is fine. Then, so you don't have to define genericity. You don't have to define G dot or anything like that. And then the forcing extension is just a quotient structure by that equivalence relation. Okay, so this is a different way of constructing forcing extensions, which is internal to the model. And that's exactly what we need, because now it makes sense over any model of set theory, even if it's ill-founded, we can do this quotient thing from inside. And this is going to give a presentation of MG. If the filter is generic, then the two constructions give you the same. So therefore, if you want to use value, if you have a well-founded model and you want to use a value recursion, then the model that you're going to get is going to be exactly the same as the model that comes out of this construction. Okay, so given an oracle for the delta zero diagram of M, I mean the set theoretic delta zero diagram of M, and we have a forcing notion P, then we can compute an M generic filter. We already saw that. But furthermore, I can give you the delta zero elementary diagram of a presentation of the corresponding extension. So the diagram. Furthermore, I can give you the diagram of the forcing extension in the forcing language, which doesn't just have the epsilon relation, but it has a constant for the ground, a predicate for the ground model, and it has names for constant symbols for every name. Okay, that's the full forcing language. And we can give a delta zero. We can compute a presentation of the delta zero diagram of that model in the forcing language. Okay. So the atomic forcing relations have complexity delta one. I mean, the set theory delta one. It's because they're defined recursively, right? It's this complicated recursion, and the reason why forcing is often found to be difficult is because even though we define the forcing relation, it's a simple recursion, except for the atomic case. So the most difficult part of it is the atomic case, which isn't often true for recursions. Usually the atomic case is sort of trivial, and then the rest of it is where the complexity lies. But the situation for forcing isn't like that. It's trivial beyond the atomic, and the atomic is this hurdle that you got to get over, and that's why forcing is often difficult. I think is precisely because of that feature. Okay, but they have complexity delta one because P is forcing sigma equals tau. It's a recursion on the names. You look at the elements, and is every element of this one forced to be equal to one of the elements of the other one, and so on. And so it turns out to have complexity delta. Okay, so therefore, given the delta zero diagram of M and the filter G, we can select representatives for the equivalence classes. Okay, we can pick representatives for each equivalence class. And then, okay, the full forcing relation for any phi is definable in the ground model, and furthermore, the forcing extension satisfies a property phi about some names, if and only if there's some condition forcing that, and therefore we reduce questions about the forcing extension to questions about truth in the ground model, and therefore. Well, I mean, we have to know how complex is this forcing relation. If P forces P has complexity sigma n, if Phi has complexity sigma n. And the reason is that you force an existential just in case there's a name that you force that name works. So the quantifiers are just matching exactly once you get for n at least one. Okay, so we can get the full diagram. If we have an oracle for the full diagram of the ground model and we have the forcing relation, the forcing notion, then we can compute an engineered filter, and we can give a computable presentation of the full diagram of the forcing extension in the forcing language using that forcing relation. Okay, and it's sort of level by level. If you want to do it for sigma n, then if you have a sigma n diagram, you can get the sigma n diagram. Okay, let's go now to the slightly different topic, what I call the generic multiverse. So the generic multiverse of a model of set theory is a kind of equivalence class you close under forcing extensions and ground models. So you can maybe take a forcing extension, and that's a model of set theory. Maybe it has a ground model. A ground of a model is just a model over which it's obtained by forcing, a set forcing. And maybe that model has forcing extension and then ground and so on, the zigzag. You close under that. That's called the generic multiverse of the model. It's all the models that you can get to by forcing, either by going up or by going down. Okay, so W is a ground of a model M if N is achieved by set forcing over that model. And it's a theorem of Rich Laver and Hugh Woodin and myself that every ground model is definable in its forcing extensions. Okay, it's called the ground model definability theorem. So the definition of the ground model uses the approximation and cover properties, which are some concepts that I had introduced in a paper of mine called Forcing Extensions with Approximation and Cover Properties. And Rich Laver saw that paper and noticed a certain consequence, and so he had approved the ground model definability theorem, and he wrote to me, and he said, "Oh, I have this theorem." And I said, oh, I can prove that theorem, and I sent him the proof using my approximation cover property, and he wrote back to me. He never showed me his proof. I've never seen his proof. And he told me that, well, obviously that's the right way to do it, and so he used my proof in his paper, but wouldn't also do it independently. Okay. The definability of the grounds is uniform. So it's called the ground model enumeration theorem, and this is maybe the beginning of the subject that we call set-theoretic geology, which is studying the structure of the grounds of the universe by forcing. Okay. I think of this as analogous to the computability case of having an enumeration of the CE sets, right? Except here we have an enumeration of the ground models. So there's an enumeration W sub R of transitive classes such that each of them is a ground model of the set-theoretic universe V, and every ground is one of them, and the relation of membership there is pi2 defined. So we have this pi2 definition of a two-dimensional thing, and the R slice is a ground, and all the grounds arise that way, and it's defined. So it's uniform.
So some fixed V, right?
Some fixed V, yeah. Well, V is. So,
Okay.
yeah. It's a ZFC theorem, so it works in any ZFC.
Right, but you want to apply it to MG.
Right. Yeah. But it's a. I mean,
Yeah.
this is a ZFC theorem. So. Okay. So, so in that sense, V means the the full universe. Okay, but of course it's interpreted in any model. So when you interpret it in M, you're talking about M.
So, but now, when you take the just a regular M, can you find the multiverse from that in a pi2 way?
That's what I'm going to talk about.
Some
Exactly.
have patience for this.
Yes. Okay, so there's a uniform computable procedure which, given an oracle for the pi2 elementary diagram model of set theory, will compute a list of the delta zero diagrams of all the grounds. I think it's exactly maybe what you asked, but actually you asked about the generic multiverse, which is sort of going up from those grounds, because this is just the grounds. That's not the full generic multiverse. You have to force over them also, and then go to more grounds. But this is sort of first step. Okay, so you give me an oracle for the pi2 elementary diagram of a model of set theory, then I can compute the delta zero diagrams of all the grounds. Okay, I need pi2 because the ground model enumeration is already pi2. So, and I mean here pi2 in the Levy hierarchy, in the set theoretic sense of pi2, not there.
This is application of previous theory.
Yes. Okay, so exactly. It's just following from the previous style. Okay, so given an oracle for the full elementary diagram, not just pi2, if I have the whole diagram, then I can compute the full diagrams of all the grounds. In the delta zero case, if all I wanted was the delta zero case, then the grounds are all transitive, and so their delta zero diagram is just restricting the delta zero diagram of the ambient universe to them, because delta zero truth is absolute between the ground models and the universe. But here that's not true. So now I have to do more work, and I have to consult a forcing relation and so on, in order to get the full diagram of the grounds. Okay, but you can do it. The grounds are uniformly definable, so any truth assertion made in a ground is just some other more complicated assertion made in the forcing extension B of that ground. Okay. So the question now is, well, what about the generic multiverse? Because so far all we've done is talk about the grounds, but the multiverse is this zigzag thing where you go to a ground and then a forcing extension, then a ground, forcing extension, then a ground. And the answer is it's uncountable. So of course you can't give a computable presentation of the whole generic multiverse. It's just too big. I mean, if I have a given model, there's continuum many forcing extensions of it. Just by adding a Cohen real, there's a perfect set of forcing extensions of it. So it's not really subject. I cannot possibly give a computable presentation of all of the generic multiverse. It's just too big. Okay, so we're gonna.
It could be Varela.
Yes, that's true. So
Is it?
well, it's. I mean, the set of forcing extensions is closed because, as I just said, I mean, to me, the dense sets is a closed property, but and then you're iterating in omega minus, so it's going to be. So, okay, I want to do it computably though, so I'm going to take a computable fragment, okay, the computable generic multiverse. So, and to do this, I'm using a theorem of Usuba, who proves that the grounds of a model of set theory are strongly downward directed, which means that if I have a set number of indices in the ground model enumeration process, then I've got a bunch of ground models, and the question is there a ground underneath them all? Is there a common deeper ground? And the answer is yes. And that was one of the principal open questions of set-theoretic geology in our main initial paper. We didn't know the answer, but I'm very glad answered it. Okay, so it follows. We had the conjecture before that it might be true, or the question whether it was true, and we knew this corollary that if it was true, then every model in the generic multiverse is, of course, an extension of a ground. So you don't have to zigzag. You just go down and then up, and that's it. And the reason is that going down and then up and then down again, well, those are two grounds of this guy, and so there's a deeper ground, so you could have gotten there just by going deeper in. So you don't ever need to zigzag, just down and then up. So the forcing extensions of the ground models is already closed underground. As a consequence of directedness. Okay, 2 steps suffice. Wooden had an observation that 3 steps suffice in his paper. I don't know why he had 3 steps. I asked him. He didn't really have a clear answer, but he, in terms of the sort of statements that could be true somewhere in the generic multiverse, he knew that you could get there in 3 steps. But it's just, in fact, this corollary is much, much stronger than that. Not just any given statement, but the models themselves can be reached in 2 steps. Okay, suppose we're giving an oracle for the full diagram. So, okay, yes.
So it must be very complicated if I give you a model M to find the kind of minimal ground inside of it.
Well, it might not exist. There's not always a minimal ground. That's called a bedrock, but not every model has a bedrock. And that's a result of my student, Jonas Reitz. He calls them bottomless models because you can keep going down forever. There's no minimum.
Okay, but to find the one that allows you, what do you call this model inside there?
Oh, the common one. Oh, I see. Yeah. Okay. So I never thought about the sort of computability aspect of that. But yeah, I think it would be difficult to find the index, right? Given 2 indices of grounds.
Yeah, I mean, because finding the extensions is easy.
No, it's not unique. Ground models are not closed under intersection.
No, but finding the extensions, the forcing extensions is always by 2.
Right.
So it's enough if you define.
That's just mainly because to find the grounds is difficult.
Right.
It's a pi 2 definition of the ground model enumeration is pi 2. So it's the difficulty isn't finding the forcing extensions because that's very easy as we saw, right? We don't need pi 2 for that.
It's for finding the common ground.
It's not unique, so it's not right to say the.
Common ground, fine.
Yeah.
So
right, I'd have to think about it. But this is pi 2 in set theory, right? It's not the same as pi 2 in arithmetic, so you can't think that.
yeah, I understand, but that seems where the complication is. Or
Right. Yeah, I'd have to think about it. So. Okay, so I want a computable generic multiverse. So we can uniformly compute the diagrams of all the grounds. If I have a full diagram of model M, then it's got a bunch of grounds in the ground model enumeration, and I can uniformly compute the diagrams of all of them given the index R. We can compute the diagram of W sub R. Okay, and then for any forcing notion in W sub R, I can uniformly compute what's true in the forcing extensions by that forcing notion for the generic filter that I would construct. So I have a uniform procedure, takes a model M, considers all the indices little r as indices for grounds, and then computes their diagrams, and inside WR picks any particular poset that you want and constructs a generic filter for it and the diagram of that model. So we're going down and then up. So this is the computable generic multiverse. We do it in this uniform way. Okay, so that's a kind of proxy for the generic multiverse, which was this uncountable thing. This is a countable structure computed from the original model, which nevertheless, any statement that is true somewhere in the actual generic multiverse will therefore be forced over some W sub R, and therefore will have built a model where that statement is true. So any statement that could be true somewhere in the generic multiverse will also be true somewhere in the computable generic multiverse. Okay, but meanwhile, it's not dense in the full generic multiverse in the sense that there's going to be some forcing extension that has no outer model whose delta zero diagram even is computable from the diagram of M. So you can, there's these cones where you're not having any computable model inside there. Okay, I don't know how much time I have.
I don't know, I mean. You have about 6 minutes.
Oh, okay, so let me not get into that. Okay, I can say a little bit more about this. So I want to get to the non-functorial part. Okay. So let me just jump ahead. Okay, we can also do similar things for class forcing and for second order, but let me get to this functorial question because I think it's interesting. So we've described how to get computable presentations of the forcing extensions from the ground model. And I want to know, is it uniform or not? The particular construction that we gave is definitely not uniform. But what I want to know is there a better one that is? So the question is, can we make a construction so that isomorphic presentations of the model give rise to isomorphic presentations of the forcing extension? And so is the procedure well defined with respect to isomorphism? Okay, so that's maybe an equivalent way to ask it is in terms of computable functors from the category of models of isomorphism. So, okay, so first is this observation that the construction that we gave, given a model M and the membership relation and P, given an oracle for that model, we explain how to find G, you build this descending sequence and take the filter generated by it and so on. That's definitely depending on how M is presented, because if I rearrange M, then the particular dense sets that show up are going to lead me to a different descending sequence of conditions. And that can definitely change G. And if it can change G, then it can change the theory of M of G, because maybe if you have this condition, you get one theory, and if you have this other condition, you get another theory. We can make forcing motions that have that problem. So the answer to the question is that the non-functorality is inherent in the process. So there's no computable procedure which takes the elementary diagram of a model and a partial order in that model and produces a generic filter such that isomorphic copies of the input always give the same filter. And let's prove that. So suppose we have a computable procedure that takes that input data, let's give it even the full diagram of the model. And it's going to produce that generic filter. And assume it's functorial. Okay. So now, take a model of set theory that has a fully correct cardinal kappa. So what I mean is that the rank initial segment M kappa, the V kappa of M, is elementary in M. Okay. You might say, oh, well, doesn't that have that has some consistency strength, right? Because if V kappa is elementary in V, then V should think con ZFC, because ZFC would be true in V kappa. And so it makes you think that it has a consistency strength exceeding ZFC, but that's wrong. Actually, a fully correct cardinal is equiconsistent with ZFC. And the explanation of it is that to say V kappa is elementary in V is a scheme. You're saying of every ZFC axiom, I mean, of every formula phi, that if it's true in V kappa, then it's true in V. And so even if it happens that V kappa, if it's elementary in V, then for every particular axiom of ZFC, it's true in V kappa, but that doesn't mean that V thinks that V kappa is a model of ZFC. If it's an omega non-standard model, it's going to have non-standard axiom, and they might not be true in V kappa. And then you can just make a simple compactness argument, actually, to write down the theory of what it's like to have a fully correct cardinal kappa. Well, we've got kappa as a constant, and we're making the assertion that V kappa satisfies phi of x if and only if phi of x. That's asserting the elementarity for every phi. That's what it's like to have a fully correct cardinal. And any finite piece of that theory is just going to be realized in the original model of ZFC by the reflection theorem. It's exactly what the reflection theorem says. that finite instances of this are adherent. The existence of such a kappa. And so therefore by compactness, we get a model with a fully correct cardinal and there's no consistency strength penalty. Okay, so we have one of these correct cardinal kappa. And now fix any non-trivial forcing below that, small forcing, and now run the computational process inside M. I mean, the computational process was for us in the meta theory, but we're going to run it inside the model, even if it's non-standard, whatever, we're going to run it in there. And we're going to use finite fragments of the diagram of M sub kappa, which is a set in M. Because M kappa is a set in M, and it proves that there's a theory it can compute the diagram inside the model. And I can use that as an oracle inside the model with this program. So I'm going to run the program inside the model using pieces of the initial segment. Okay, and if it gives me an output, then that output has to be part of what could have been a presentation of M itself, because it stopped at some finite stage. And so whenever that algorithm said that a particular condition was in the generic filter, then now I look at what it used of the oracle and I rearrange everything to make a presentation of M, and therefore by my assumption that it was functorial, I can see that running the program on M itself in the meta theory would have also put that very same condition into the generic filter. So the point is that therefore the process of producing the filter could have been run inside M, and therefore the generic filter would be in M, which is not possible because generic filters are never inside the models over which they're generic. Okay, so but meanwhile for some models we can compute the generic filter functorially from any presentation. So this is a slight nod in the positive direction. And the theorem is that if you have a pointwise definable model, then it has this feature of functorality. It doesn't matter how you're presented, you can always pick out the same generic filter. And the reason is that if it's pointwise definable, which means every element is definable without parameters, then it provides a canonical.
Give a good example of such a model.
Yeah, the minimal model, the Shepardson-Cohen model is pointwise definable.
I forget what that is.
That's the least L alpha in the constructible hierarchy. That's the ZSC model. So that one's pointwise definable. So also, if you take any model of equal hot and look at its definable elements with no parameters.
Using basically instructability, if you will, in some sense.
Yeah, but I'm giving you a more general argument now. Just take any model of equal hot, and that's forcible. Any model of equal hot. Take its definable elements without parameters. But CFC plus equal hot has definable Stone functions. So it's an elementary substructure. The definable elements are elementary because it's closed under the Stone function. And therefore, if I just take the definable elements, it's elementary and they're all still definable in that one. So that's a pointless example.
That's also not, there's all that reason.
Okay, so there's a computable functor which takes as input the elementary diagram of any pointwise definable model, and we have tons of them, and a forcing notion and returns a generic filter. And if you gave isomorphic presentations as input, you're going to get isomorphic output, in particular the same generic filter. And we've extended this by a much more complicated argument to the Borel case. So there's no Borel function that produces them generic filters in a functorial manner. And furthermore, the argument even shows the following: there's no Borel function, so that if you give me two presentations of elementary equivalent models, then the forcing extensions are elementary. Okay, but if you go up to projective, so beyond Borel into the projective hierarchy where you allow quantifiers, okay, I think this is the last one. Then we can get it. So there is a projective functorial process that produces these forcing extensions in a way that respects isomorphism. So okay, that's it. Thank you very much.
Any more questions? Peter?
So, back to what you're saying, the value approach, you couldn't work with you gave up on it from working with the ill-founded models. So are you guaranteed that at least outside, because that ill-founding is like, sufficiently, fully definable. So for instance, you could use the induction to show that, the induction still works, because the ill-founded chain is sufficiently non-definable, or could it be definable?
Oh, I see. Well, that's a really good suggestion. I haven't looked exactly at that, but one remark to make is that because we have this other construction, and then inside the forcing extension, then the value construction makes sense again. And so I think maybe one could answer your question by thinking about how complex. In other words, you start with M and you want to build M of G, and the normal way to do it is with this value thing, but that doesn't make sense if M is ill-founded. So we have this other way of building some other M of G by the quotient, the Boole-Northborough quotient construction. But then in M of G built that way, we can now, that provides a meta-theoretic context for doing the value construction. And I think it would give an answer to your question, but I haven't thought about it exactly.
Thanks.
More? Well, let's thank Joel again. Thanks. No, he's gonna be gone.
Oh, he is, okay.
What's it? What?
I just didn't get in trouble. So yeah, here's the.
I'm working on it.
Here's the.
Where is it?
We got B jump was in. If you want to make sure that if that happens, then we show that, A